Hello 8th graders, in this IXL video we're taking a look at assignment G3, which now that you're more familiar with scientific notation numbers has you start adding and subtracting numbers that are written in scientific. Before we dive into these examples, we just want to go over some ideas about if you're asked to add or subtract numbers in scientific notation, our strategies for attacking the problem. There's really two types of scenarios you'll run into. The simpler or the easier situation is if they ask you to add or subtract scientific notation numbers that have the same powers of 10. If they have the same power of 10, all you need to do is add or subtract the coefficients, and then that power of 10 stays the same. If they have different powers of 10, it's probably a tougher problem to add or subtract, and you have two options if the powers of 10 are different. One option is to switch them or convert them into standard form, the way we've always written numbers, and then just add or subtract, but it's going to be a big long number. The other option is more complicated idea at first. You can switch the numbers or transform them to have the same power of 10, and we'll talk about that when it comes up. So here we see we're told to subtract, and then we're going to write our answer in scientific notation. And we do see right away as we look at the two numbers we're subtracting. I'm going to zoom in a little bit. As we look at these two numbers that we're subtracting, they have the same power of 10. That's an important thing to notice. When I have the same power of 10, I can just add or subtract the coefficients and keep the power of 10 the same. So in this case, I'm really just going to be doing 6.63, and I'm going to be subtracting that 2.6 away from it. And I should probably have a whiteboard out, and I'll switch to that for the next problem. But I'm going to go ahead and do 6.63 minus 2.6, and at the end of the day, that's going to give me 4.03 when I do that subtraction. We'll switch to a whiteboard for the next one, I promise you. So if we go to 4.03, what we need to remember is now, hey, we had 6 sets of 10 for both of these. So we're still going to have that same 10 to the power of 6 here. That's not going to change. When you see the same powers of 10, you can simply add or subtract the coefficients, and that power of 10 stays exactly the same. So in this case, the answer that we need is the 4.03 times 10 to the power of 6. And we see that's the correct answer. Right, and for our next problem, we see subtract, write your answer in scientific notation, and we do see they are the same power of 10 again, which means we will have a bit of a shortcut. We can just subtract the coefficients and keep the power of 10 the same. So because these do have the same power of 10, I can really just take these two coefficients you see on my whiteboard now and subtract those coefficients. So I set up, I'll call this the standard algorithm when you stack them up and subtract the way you learned in earlier grades. And I'll go ahead and follow that algorithm to see here when I do this subtraction out, I get 3.32. Now as I look at my answer choices, we see there are two options that have that 3.32. But recall, if we subtract and they have the same power at 10, we subtract the coefficients, but we keep that power at 10 the same. So in this case, we're going to have 3.32 times 10 to the power of 4, since both of these were 10 to the power of 4 numbers. And now we see for the next question, once again, they're giving us the same power of 10. And that means we're just going to keep the power of 10 the same, 10 to the power of 7. And if I do 4 minus 2.1, I get 1.9. I kind of know that already. And I'm not going to have 10 to the power of 0. Recall the power of 10 will stay the same, so I'm just going to go 1.9 times the power of 7. Now, here's our first example of an addition one, and we'll see something else come up that's a little tricky here. So we do see same powers of 10 again. Anytime it's addition, subtraction, and you see the same powers of 10, you can simply add or subtract the coefficients. In this case, we're being asked to add, so I'm going to go ahead and do addition with 4.2 plus that 8.1. And if I follow the algorithm, that gives me 12.3. Now recall the power of 10 stays the same, so this is 12.3 times 10 to the power of 9. But when I look at my answers, I don't see the coefficient 12.3 anywhere. I see 1.23, which is very similar to 12.3. It's just a power of 10 smaller, where the decimal points move. And that's actually going to be one of our answers. What we see here that's important, sometimes when you use this addition rule, you're going to get the coefficient end up being too large for scientific notation. Scientific notation requires that this coefficient be less than 10. So in this case, I'm going to have to convert 1.23 is what I would get if I move this decimal to the left one place. And now I would have a coefficient that's less than 10 like we're required to do. But because I stole a power of 10 from here, I divided by 10 basically. 12.3 divided by 10 is 1.23. I need to have an extra power of 10 here to keep everything equivalent. Because if I take this one extra power of 10 and I put it into here, I'd be back to 12.3. And then I'd have 9 tens left over. So sometimes when you use the shortcut to add or subtract the same powers of 10, you have to take one extra step to see what would the scientific notation number be. In this case, it would be 1.23 times 10 to the power of 10. And now we see here our first example where we see a different power of 10. They're asking us to subtract these two numbers, but they do not have the same power of 10. So there's really two options to approach this problem when they have a different power of 10. Option 1, you can always switch these over to standard notation numbers and add or subtract. So if I know that 1.2 times 10 to the 7th is the same thing as 12 million. And I knew that by moving this decimal 7 places to the right. You see, I get a 12 with 6 zeros. That's what happens when I go 7 places to the right. And I also know that the other number, 9 times 10 to the 6th, the coefficient's bigger, the power of 10 is smaller, though. So 9 times 10 to the 6th is actually a 9 with 6 zeros attached to it. Or the number 9 million. And once I have these switched over to standard form, so long as I line up my place values, keep the commas stacked up, I can go ahead and use the standard algorithm to add this large number. 12 million plus 9 million is just going to give me 21 million. And I'm making a mistake here. This was a subtraction problem, not an addition problem. So I'm going to go ahead and subtract instead of adding. My fault there. And we see 12 million minus 9 million would leave us with 3 million. I caught that mistake, by the way, as I looked at the answer choices. None of them lined up with my 21 million at all, and I said I better double check. I said, oh, this was subtraction, not addition. But here we see, okay, which one of these answer choices is 3 million? There's only one option with the coefficient of 3, and it does turn out 3 times 10 to the 6th is going to give us 3 million. Now, that was quite a bit of work to write all that out to find 3 million. There is one other method you could take. That's what's listed here on our notes on our screen. If you have different powers of 10, you have two options. We just showed you the first option in blue, convert to standard notation, then add or subtract. And I'm going to use this red marker here to show us the other option. We could have transformed so the powers of 10 are the same. Up here we see that these are not the same power of 10. We're going to be subtracting them, but they're not the same power of 10. However, if they were the same power of 10, we would be in good shape. We could subtract with a nice shortcut. And what I recognize, I'm going to get this 10 to the power of 7 number to be a 10 to the power of 6 number instead. I'm going to steal one of the 10s from here and multiply it with the coefficient. 1.2 times a 10 would give me 12. And it's important to know that 1.2 times 10 to the 7th, even though this is not scientific notation, when I say 12 times 10 to the 6th, they're equal to each other. And now if I had that, I would have 12 minus 9, which just gives me 3. And we could use that shortcut there when we have the same powers of 10. We can just subtract the coefficients, and we get that same answer, 3 times 10 to the power of 6. And again, this is quicker in red, but I had to understand how to switch 1.2 times 10 to the 7th into 12 times 10 to the 6th. It's equivalent version that had the same power of 10 as the number we're subtracting. So I think the blue method is more tried and true. It's straightforward, it would work, it takes some time. And I think the red method is a beautiful way, if you understand powers of 10, to save yourself some time. And for this, there is no challenge zone. They just kind of progressively make the problems more difficult as you go. So I'm going to show one or two more problems, but I do believe you're in perfect shape right now to stop this video and be doing IXL work on you. I'd encourage you, if you're still with us, if you're going to watch this problem, pause the video and think about how would you handle this 2.8 times 10 to the 9th plus 3 times 10 to the 8th. And as you're coming back, I would emphasize this is a situation that's tougher because some of you may be saying we have a different power of 10. 2.8 is times 10 to the power of 9, or a billion, and 3 is multiplied with only 10 to the power of 8, or 100 million. So if we're being asked to add these two numbers together, we have two options. I'm going to put option 1 here in blue. We could switch these two numbers. They have different powers of 10. We could do the long way of switching them into standard notation. 2.8 times 9 copies of 10. Saving us a little time here. It would take you a little while to work that out, I think, but it would give you 2.8 billion. I do know 10 to the 9th is billions. That's what saved me time in writing that up. And if 10 to the 9th is billions, that means 10 to the 8th, one less, is going to be 100 millions, or a 3 with 8 zeros attached to it, is really the number 300 million. And now once I've converted those two numbers into standard form, all I need to do is add by using the algorithm, making sure that the decimal points and the commas are stacked up. And I get at the end of the day, these zeros aren't changing. But we do get 3,100 million. And if I look through the options, we will see there's two of them that have a 3.1. One of these is going to be correct. I do know 10 to the 9th is billions. I'm thinking this is correct. But I'm going to try the other method here now too. In red, I'm going to convert. I want these to be the same power of 10. So I'm going to go ahead and I have two options. I could take this guy and make him go become power of 8. Or I could take this guy, bump him up to power 9. When I add, I like to take the smaller number and bump up its power of 10. It's your choice, either one works. But if I'm going to switch this to 10 to the power of 9, that means I need to steal a power of 10 from 3. And it's going to be 0.3 times 10 to the 9th. That's the same thing as 3 times 10 to the 8th. I took a power of 10 away from the 3, divided it to 0.3, and that power of 10 now shows up in the exponent. And once I've done that, now I have 2.8 times 10 to the 9th plus 0.3 times 10 to the 9th. And so the same power of 10 just stays there, and all I need to do, 2.8 plus 0.3 gives me 3.1. So now we see in red there the same answer that we had in blue, but it's in scientific notation. And it may have been easier, less writing, less work, if we understood how to switch 3 times 10 to the 8th, a 10 to the 9th number that's equivalent in value. I'm not going to keep going at this point. The video's up to 14-15 minutes, so we're kind of going to stop here. But you see there's two methods, two basic methods for attacking addition and subtraction problems. If they're in scientific notation, when they're the same powers of 10, it's quick and easy. You just add or subtract your coefficients. If they're different powers of 10, you need to choose between converting the numbers to standard form and adding them up, or getting them to the same power of 10 so you can use that shortcut we talked about earlier. Thank you for watching to the end of the video. If you do have any questions, as always, please feel free to email me.